So we're here looking at sequential games like chess, where one player gets to act first and then other players act after that, and potentially with several steps. It's from my textbook in microeconomics, and I'm Richard Friedberg. Okay, and we're going to be doing this in the context of a game of chicken, as it's known. Okay, so just to introduce the payoffs and the setting, we can first think of the case where this, if this were a simultaneous game where two players were choosing strategy at the same time. So the two players here being Buzz and Jim, 1950s kind of setting, sitting in each of their cars, pondering whether to drive straight towards each other or to swerve, to chicken out. So the payoffs are dependent, of course, of their own strategy. Taking Buzz's stand here on Buzz's strategy, driving straight or swerving, and on Jim's strategy, driving straight or swerving. So if both drive straight, bad outcome here. With parameterized that, we set the number to -10 here. We could think of larger numbers, larger negative numbers, but of course, in this kind of setting, it's only the ranking that matters. So they both crash here. If Buzz swerves, whereas Jim drives straight, Jim gets a positive payoff, whereas Buzz is the chicken. Okay, so he's showed that he's chickened out. He was weak. Okay, or vice versa. If Buzz drives straight and Jim chickens out, the payoffs are reversed, and if they both chicken out, the payoffs are normalized to 0. Okay, so they get, it's a live and let live kind of strategy where neither loses in relative ranking. And this is what we could call an asymmetric coordination game if it's played as a simultaneous game. We have two sets of equilibria, swerving, no swerve. Okay, but that's not where we're going. We want to see how can we solve this game if it's played as a sequential game. We could be discussing, based on the matrix, we could say that if Buzz were to drive straight, we would essentially close off the lower part of the matrix here. But we might do this in this simple case. But more generally, we want to introduce the tools of how can we analyze sequential games. We're going to be using a tool called a game tree, or the extensive form of a game is often used, even though that doesn't necessarily. Game tree is more descriptive, I would say. Okay, so we're moving as we're writing in English from left to right. So we're starting with the first player, so Buzz. So player 1 ready. We're depicting branches of the tree here. We're using branches to depict the different strategies that Buzz has. So if there were 3 strategies, there would be 3 branches. So Buzz can choose to drive straight, just right straight here, or he can swerve. Okay, so here you could think of this as a commitment to driving straight or to swerving, putting wielding the steering wheel shut, putting a big rock on the gas pedal, moving back into the back seat would be associated with driving straight, for instance. Okay, so first, the first player gets to choose first. Let's sort of, you can hear that. Then we come to the second player. So we write the name of the second player at this node, so we time 0, time 1, and then it's time to depict Jim's different choices. So these could be in principle different depending on where we are in the game. So the set of strategies that are available to Jim after Buzz has driven straight might be different from the set of strategies that are available to Jim after Buzz has swerved. But In this case, they are not. Okay. So we look at the payoffs. And the convention is that we write the payoffs of the last player to play last. So we would have a payoff of Jim. And we would have the payoff of Buzz. Okay, so if Buzz has driven straight and Jim has, let's see, also driven straight, should write these, straight or swerve, straight, swerve. So swerve, you know, avoid a collision, doing the sensible thing, but not necessarily in this game. Okay, so payoff if straight and straight, this is -10 for Jim. And we'll go ahead, straight and swerving for Jim, -5. We'll write Buzz's corresponding numbers here. So -10 here and 5. Continue with Jim. So if Buzz, or continue here, if Buzz swerves, Jim drives straight. -5. Here we have 0. And then we have 0 there as well. And here we have +5. Okay, so now we've described the game. We have the players, we have the set of strategies, and we have the payoffs. What we do when we write the game tree, as opposed to the payoff matrix, or in other words, what we do when we have the extensive form rather than the normal form, is that we account of time. Okay, the sequencing of moves. So how do we solve this? Well, look ahead and reason back is the way that we typically think of this. So we start from the end. We start with the player who is the last to take action and see what he would choose, or he in this case. And as in the normal form game, we walk through all the different possibilities, and we can show this in different ways. Just like we underline, we do various things. We can set arrows, etc. But one way is sort of closing a path. So here we're starting from the end, looking at reason back. So Jim, in the case where Buzz first has driven straight, is comparing payoffs -10 to -5. So neither is particularly attractive, but -10 is even worse than -5. So we close this path. Okay, we believe that if we end up here, Jim will choose to swerve, since -5 is better than -10. Continue down here. What if Buzz would have swerved in the first, when he first had the move? Well, what would Jim be facing then? Well, he would be facing the choice between 5 and 0. 5 is greater than 0, so we close this path. Okay, so we've looked ahead. Now we reason back. We're Buzz here. So he's thinking, should I drive straight or should I swerve? What's the payoff what's the predicted payoff if he drives straight? Well, we would then be expected to be down in this branch. We've closed this branch. So the expected payoff here would be 5 for Buzz. Okay, so he's comparing that with swerving, where the expected payoff would be -5. 5 is better than -5. So we close this branch. And this then is the predicted outcome in this sequential game. Okay, with a fancy word, we call this a subgame perfect Nash equilibrium.